This paper is entitled Solvent Emission Reduction in the Modern Environmental Laboratory. Authors William R. Jones, Lindsay Holcroft, and Zoe Grosser. The outline of this talk will cover the Clean Air Act with Title V permits, a background on solvent reduction, reducing solvent emissions by several approaches, discussion of the liquid extraction technique and then migrating over to solid phase extraction, means of solvent recovery, and then a review of the conclusions. Title V emissions of hazardous air pollutants, HAP, has a stated potential limit of 10 tons per year and a combined HAP potential maximum of 25 tons per year. Individual states have implemented a version of the Title V regulations. Most have adopted the Title V amounts, but others have implemented their own limits. For example, Massachusetts requires a single HAP potential emission of 1 ton per year. The Environmental Analysis Lab has a number of HAP solvents to consider, but the solvent most used and therefore of major concern is dichloromethane, DCM. For extremely small emitters, no permit is required if they are not at risk of exceeding the individual state limits. In 2014, 4 labs in Massachusetts were fined for exceeding the HAP emission limit without a valid permit. The fine was $350,000 per site. The concern is that other states will become more stringent, in which case a reduction in solvent use and/or more effective recovery would be required. Liquid extraction, LLE, utilizes large volumes of DCM per sample and is the most commonly used means for sample preparation. A 1 liter water sample is extracted under basic conditions with 3 60 milliliter aliquots of DCM. The water is then re-pH'd to acidic conditions and extracted 3 more times with 60 milliliter aliquots of DCM. The extract is collected and dried over sodium sulfate, where the container has to be rinsed to ensure that there's full quantitative transfer, along with the sodium sulfate to be rinsed with DCM to make sure that recovery of the extract is complete. After which, evaporation of over 360 milliliters of DCM down to 1 mil is performed. An internal standard is included into the extract, transferred to a GC vial, and then only 1 microliter sample is injected into the GC with a split. So this translates into over 360 milliliters of DCM per sample. 1 ton of DCM translates to about 1,895 samples, or roughly about 7 samples per day per year. How to reduce solvent emissions? There are 3 ways. Reduce the sample size collected, reduce the extraction solvent needs, and recover solvent used. In reducing sample size, the 1 liter sample size was set decades ago. It was based on concerns on sample homogeneity and analytical instrument sensitivity. Nowadays, sample homogeneity has been shown to be less of a concern than originally thought. Analytical instruments sensitivity is dramatically improved, and the benefit of lower sample shipping costs and reduced hazards are driving lower sample collection down the line. And it's possible to do additional sampling at a lower cost if you're dealing with smaller samples. EPA methods are acknowledging smaller sample sizes as they are being updated. Method 521 in the year 2004 specifies 500 milliliters of water. Method 535 in 2005 specifies 250 milliliters of water. Method 522 is 100 or 500 milliliters of water, depending on the SP sorbent chosen, and method 3511 is down to 35 milliliter sample size for micro extractions. And method 625 is flexible in sample volume based on the detection limits needed for compliance. Manufacturers have improved sensitivity over the past few decades. The injection split ratio can be changed to improve sensitivity. SIM, selective ion monitoring, can be used, especially now that scanning can be used simultaneously with SIM. Triple quad MS systems are now offering increased sensitivity, and large volume injection is becoming more common for the older systems. Injection volumes of up to 50 microliters are now possible. Reducing solvent usage with SPE. Smaller samples require less solvent for extraction. Solid phase extraction, SPE, requires less solvent for analyte elution compared to LLE. In summary, water is passed through the SPE disc and analytes are retained. The analytes are eluted with a small volume of solvent. Depending on sample complexity, 80 to 180 milliliters of solvent are needed for elution compared to the 360 for a typical base acid neutral liquid-liquid extractions. This slide shows the development chronology for semi-volatile organics in wastewater for the performance-based method 8270D. The SPE method shows the increased analyte capabilities over time by migrating away from a single-mode media, DVB, to a custom mixed-mode media in the 8271 pass disc that employs HLV and ion exchange. In addition, traditionally difficult to retain compounds such as NDMA are quantitatively captured using a custom carbon cartridge that scavenged the effluent from the 8271 pass disc as the sample water was directed to waste collection. The term one pass means that the acidified sample is passed through the disc only once and onto aqueous waste collection. Eliminated is the need to collect the pass-through sample for a basified, high pH, second pass through the disc to capture the organic bases. In 2012, we demonstrated that the method could be performed without compromise with 1/10 the sample volume. This translated in lower operating costs, faster processing times, and importantly, lower solvent consumption. For the traditional 1-liter wastewater samples, an easy flow disc holder that houses a 47 millimeter disc and a sample reservoir that uses 100 millimeter filter discs to permit faster sample flow through the disc when the samples are laden with solids. The extraction volume is 200 milliliters and is evaporated down to 1 milliliter. A 1 microliter injection is performed onto the GCMS with a 10-90 split. And 1 ton of DCM would represent about 3,400 samples, or about 13 samples per day for a year. Using only 100 milliliters of wastewater sample and a standard 47 millimeter disc holder, the extraction volume is 80 milliliters and is evaporated down to 1 milliliter. A 1 microliter injection with no split maintains the same mass loading into the GCMS without compromise to detection sensitivity. So 1 ton of DCM now would represent over 8,500 samples, or about 33 samples per day for a year. With regards to solvent recovery, the less solvent that needs to be evaporated to obtain the sensitivity needed in the analytical step, the less that might be emitted. Recovery of evaporated solvent is the last step to consider in the full process. Consider the potential for recovery when purchasing evaporators. Evaporators that combine water vapor and high nitrogen consumption will make solvent recovery challenging. Let's consider a closed evaporation system. The dry vap evaporation system evaporates up to 6 200 milliliter samples at once. With the solvent trap SVOC condensing kit incorporated with the unit, the cooled glass column condenses more than 95% of a variety of solvents. If this is applied to liquid-liquid extraction, the 1 ton limit where solvent wasn't recovered for DCM translates into about 7 samples per day for a year. Or with the solvent recovery system, as shown here, about 146 samples per day for a year would be achieved when reaching the 1 ton limit. In a batch process experiment test of 1,200 milliliters of DCM, which was 200 milliliters per evaporation tube, under the operating conditions shown, the run time was under 50 minutes to get the sample volume down to 0.9 milliliters in each of the evaporation tubes. The recovery was 97.4% of DCM, with a standard deviation of 0.270, which was achieved by running this batch process 5 times, spanning over 2 days with 2 operators. benefits of solvent recollection. The solvent trap SVOC system allows facilities to prevent harmful solvent vapors from being released to the atmosphere, collect solvents for proper disposal or potential redistillation and reuse, and protect workers from exposure to harmful solvent vapors. What to do with the collected solvent? It can be disposed through proper channels, it can be redistilled to the quality required by the lab, or it can be sold to other facilities for different uses requiring less quality, such as metal finishing. This video clip shows the collection of dichloromethane from 6 evaporation tubes containing 200 milliliters each. The yellow color is attributed to the 50 microliter spike of 8270 analyte mixture. The dry-vap solvent trap SVOC system's advantages include typical solvent volumes of 180 to 200 milliliters of DCM can be evaporated in 50 to 60 minutes run time. The endpoint can be automatically detected and the process ended when the endpoint is reached. The sample can be evaporated directly into GC autosampler vials, eliminating transfer from the evaporation vessel. An excellent solvent recovery for disposal or reuse. Difficult samples such as soil extracts can also be done on the dry-vap solvent trap SVOC system. Excellent solvent recoveries were obtained along with good analyte recoveries with these particular matrices. This chart shows the excellent recovery of 8270 analytes. 50 micrograms of each semi-volatile organic analyte was spiked into 6 200 milliliter volumes of DCM. In conclusion, advances have been made that allow the reduction of solvent use in the laboratory. For smaller sample sizes, this means less solvent needed for efficient extraction, and more sensitive analytical techniques reduce the need for larger samples. With solid phase extraction, this reduces solvent needs for effective extraction of small and large samples up to 1 liter. Solvent recollection is feasible, and instrumentation has been developed to recollect more than 95% of many solvents. The trend of using less solvent will continue until the limit of feasibility is reached.